with the camera.
Forgot my
Wait,
camera was still on. Yeah, I've got the annoying like bottom of the screen camera. So you both get this very weird view of my face and also yeah. See, I, it's even worse because I have a touch screen. So if I'm ever trying to like draw something on the touch screen, the view is
oh
just
yeah.
oh now I feel self-conscious. I'm gonna mute myself or turn off my again. Also, you're all gonna see if I'm like slacking off and
Right. That's um
Oh, I guess, yeah, you asked if there was anything I wanted to say.
oh yeah, yeah.
I guess a couple things. Just a reminder, there was like a survey that we sent out. You don't have to fill it out if you don't want to, but like for the people who do have any ideas or any feedback or whatever, I'd suggest doing it. It's only 4 questions long. We've already gotten a few pieces of interesting feedback that might help us determine what to do in the future. You might have seen the lecture 1, the recording is online. And then for those of you who missed it, I sent out Ryan's lecture for his paper with Zhongwan Ha and Matt Hastings on their LDPC code. So his lecture is online on YouTube. Just a general rule of thumb, like if you've never seen a Ryan O'Donnell lecture, you should just watch as many as you can. They're all just like fantastic. And so even though we haven't gotten there in the reading group to understanding like what's a fiber bundle or whatever, it's still like a very clear lecture, and I definitely recommend watching it. So yeah, I think that's all I have to say.
Okay. So I guess I'll get started then. So I was going to do the toric code, but I think maybe I'll start with a little bit on stabilizer codes, because last time, if I recall correctly, we kind of did the 9-qubit code, but we didn't talk about the general formalism that much. So this might be a review for a lot of people, but what is a stabilizer code? Well, a stabilizer is just, it's going to be a tensor product of Pauli operators. So assume that everyone knows these. Just to remember, you know, x z is iy, and you know, xz is minus cx. They all pairwise anti-commute, and they square to identity. So stabilizer is something that looks like, I don't know, like x, tensor pi, tensor y, tensor z, tensor blah, blah, blah. And then why are they called stabilizers? Well, a stabilizer code is specified by a collection of these things. So each of these, you know, it has eigenvalues plus or minus 1. So a stabilizer code is, I give you a collection of these things, say S1 up to SK. The associated code is just the subspace of all the states that are stabilized by these. That means that S1 psi, S2 psi equal to dot, 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 SK psi is equal to psi. So this is the subspace that's the common +1 eigenspace of all k of these things, of these stabilizers. You know, it's sort of clear that if you have an S1 and an S2 and psi is in the +1 eigenspace of both of these, it's also in the +1 eigenspace of the product of the two of them. So these things actually generate a group. So you can, by taking products, and so you can talk about the stabilizer group. So these. Another thing you can see is that any two stabilizers either commute or anti-commute. So for all stabilizers And that just follows from the fact that the Pauli matrices either commute or anti-commute, and then these things are just tensor products of Pauli matrices. So if you pull them past each other, you might get a phase from every tensor factor that an anti-commutes, and then you multiply them together and either get +1 or -1. So that implies that we can use it to show that all of the basically all the stabilizers in a stabilizer group that correspond to a valid code, like code that's not like the trivial subspace, they all have to commute with each other. So I'll just say that yeah, so for non-trivial code, basically two conditions that all the stabilizers should pairwise commute, and then that minus the identity operator is not in the set generated by these guys. Okay, so the second condition doesn't matter so much because today I'm not going to talk too much about general stabilizer codes, just a particular one, but there's something to keep in mind that you want the stabilizers to all commute with each other for you to have a meaningful code. So why, I guess like how does this relate to like the notion of error correction? Well, here's sort of how. So I guess you could ask, how am I going to do error correction if I have a set of stabilizers? So I have S1 up to SK. So first of all, let's just imagine that I'm working on n qubits. Oh, just qubits. And it turns out that every stabilizer that you throw in will reduce the dimensionality of the space by a factor of 2. So it like subtracts a qubit, because every stabilizer sort of, half of the, like very roughly speaking, like half of the space is like the +1 eigenspace and half is the -1 eigenspace, and you're killing off half every stabilizer you add in. So you can show that if you have k stabilizers and they're in some sense independent from each other, then the dimension of the corresponding code is, I guess, 2 to the n minus k. So that means that you can think of this as a code with n physical qubits and n minus k logical qubits. Okay, then how does this correct for errors? Well, for this to be an error correcting code, that means if I start with a state that's in, let's say like error correction. I start with the state psi, it's in C, and then I apply some error EI to psi. I should be able to detect it if that error is small enough, if it only acts on a small enough number of qubits. So should be correctable if EI on few qubits. So I guess one thing John mentioned last time is that you can show that it sort of suffices to consider errors that are themselves tensor products of Pauli matrices, because any general error can be written as a linear combination of such matrices. So without loss of generality, EI is a tensor product of Pauli's So how can I, what does it then mean for EI to be correctable? Well, what's a way in which EI would not be correctable, right? Is if EI psi, psi started out in the code space. If EI took me to some other state that's in the code space, it'd be bad, right? Because then there's no way I could tell that this EI psi is not some encoding psi prime of some other valid state. So there's no way in principle that I could correct for EI. So implies EI is not correctable. And trying to figure out how I want to say this. Yeah, let's just observe another thing that if EI doesn't commute with one of the stabilizers, let's say there's some so remember, because it's a tensor product of Pauli's, the only possibilities are that they either commute or they anti-commute. So let's say it anti-commutes. Then we can maybe not necessarily correct for EI, but we can at least detect EI. And why is that? Well, you can just take a state psi and suppose psi is a valid code state, so it's in the code space. Then if you measure any of the stabilizers, since this is in the code space, then by definition, the measurement outcomes will always be +1 with certainty. Right, so you can measure these things without disturbing the state at all, and you know exactly what outcome you're supposed to get. And now, if an error EI has occurred, if you measure SJ on the state EI side, I think you will get basically this won't be the case. So you'll get a different outcome. So we can calculate the expectation value. So what we've shown here is that if an error occurs that doesn't commute with one of the stabilizers, now because we've assumed that the errors are all Pauli, that means it has to anti-commute with that stabilizer. Then if I measure that stabilizer on the state, instead of getting the outcome +1, which I expected to get, I'll actually get -1. So this tells me that an error has occurred, right? So that means I can detect EI. So motivated by this, we basically call this process of like measuring the stabilizers and checking that we get the outcome +1. We call this a syndrome measurement. So if you get anything other than +1 for all your measurement outcomes, you know that an error has occurred. And then you can try to correct the error based on the measurement outcomes you got. So I guess there's a step that I kind of want to skip over, but I guess what I want to say is that so it doesn't commute with these stabilizers. We know we can catch it, right? We know we can at least detect that an error has occurred. The kinds of operations that can occur that are dangerous are things that commute with the stabilizers, but are somehow, they somehow change the underlying state, right? Because those are things that will never show up when you do a syndrome measurement, so you won't detect them because they indeed keep you within the code space, but they might change the encoded data. So these are the dangerous things. And these are what are called the logical operators. This is basically any E such that really what you want is that EI psi acting in a code state is in the code space, but it's not equal to psi, some other state in the code space. And what that means in terms of Pauli's, if E is a Pauli, is that E should commute with every stabilizer SI, but it should not be generated by the stabilizers.
And Anand, the quantification of that, is it for every psi, E psi is in the C, but not equal to psi? Or is it just like there exists a psi where it's in the code space?
I guess the top one should be for all psi. Let me think about this. I think actually,
or are they like the same?
Okay, so for the bottom one, it should be there exists a psi. Because you could imagine, like, say the logical Z operator. It's supposed to do a phase flip if you have a logical 1 state. But if you have a logical 0 state, then it won't do anything. But it's still bad. It's still a potential error that we can't correct. So that's why I think it's an existential on the bottom one. For the top one, I think if you restrict to Pauli errors, it probably doesn't matter. Like I think any Pauli is either going to commute with all the stabilizers or anti-commute with one of them, at least one of them. And if it anti-commutes with at least one of them, it's just going to take all the states out of the code space, I think. Okay, so this is the condition that, so these are the kinds of Paulis that can actually change the encoded data. Yes, those are the kinds of things that we can't correct. So I think that's actually kind of enough stabilizer theory to begin talking about the toric code. But are there any questions about any of this stuff?
I mean, I guess we still haven't talked about how many errors you can actually correct with a code like this.
Yes, good. So I can actually say that now, and then we might. I thought it'd be easier to say this with the example, the toric code, but I could. So like the notion of distance. So I think what you're getting at, right? Basically, so remember classically the distance was like the minimum weight of like if you have a linear code, it's like the minimum Hamming weight, or I guess for any code, it's like the minimum Hamming weight between two strings in the code, right? So like the minimum number of bits you need to flip to go from one code word to another. So here, for these things, it will be the minimum. So I think, let me just introduce some notation. So this will be, whatever, I don't, so let's just call this like this is like a notation that I'm inventing on the fly here. So I don't know what people actually call it, but I'm just using this to denote the set of logical Paulis for a given set of stabilizers. So the notion of distance is just the minimum weight I think of any operator in this logical set. And so that I'll call D, and then you can.
Sorry, is this set not the same as just the group generated by S1 through SK? Like what's the?
No, it's the normalizer. So it's everything in the Pauli group that commutes with S1 through SK minus the group generated by S1 to SK. So everything that, yes, it's like these two conditions here.
Okay.
It's the set difference, crucially.
Right.
Between the normalizer and the minimum generated group.
Yes, that's right. Actually, let me write that down so that the logical is defined as the normalizer set minus the group they generate. So going back to the distance.
Sorry, it's the centralizer minus the subgroup. The normalizer means you commute with the subgroup by itself, but here you have to commute element-wise, so it's a centralizer.
I see.
I always forget these definitions. I had to look up the Wikipedia.
Aren't they the same though for the case of these?
I think that's what it says in the Dan Brown notes. In general, they're not the same, but like for stabilizer codes, they are.
Okay, so I'll say centralizer or normalizer. Yeah.
Sorry, what's the formal definition of either of those?
I think the centralizer is if you have a subgroup, so you have G and then you have like H is a subgroup. What's the notation for subgroup? I always forget. Is it like that symbol?
That's a normal subgroup.
Oh, that's a normal subgroup.
It's just less than or equal to.
Just less than or equal to. Okay. So the centralizer of H is like the set of all G in G, such that for all H in H, GH equals HG. Right? Okay, Chinmay, you can correct me if I'm wrong here. And the normalizer is just the set of all G and G such that G acting to the left on the set H, it gives you a set of things that you may have permuted them around, but it should still be the same set that you get the other way. Is that right?
Okay, nice.
Yeah.
Thanks.
Okay.
And for stabilizers, they're the same.
I think so. I think it doesn't make a difference which one you use.
That's interesting. Cool, thanks.
Sure. Okay, so that was the definition of logical operators. But I think what I wanted to say here is that if this is how you define the distance, then you can correct errors up to weight. I hope I get this right. I think it's floor d minus 1 over 2. Because the idea is that if you have an error that occurs, you find some sort of correction for it, and then you don't want it to happen that your correction multiplied with the error actually gives you something in the set of logical operators, because then you will have, instead of undoing the error, you will have actually like done a logical operation. And I think if this is the case, you won't do that. But yeah, someone should check me on this. But I think it will not be too important for what follows.
I mean, d over 2 is the right asymptotic, whether it's floor minus 1 or whatever is.
Yeah,
not quite as important.
that's true. Yeah. Okay. So, okay, I was going to move on to the toric code, but I'll pause again if there are any more questions about this stuff.
Oh yeah, can I ask a question?
Sure.
So this seems to be a major change of language from classical codes, right? I mean, classical code is like the distance is the minimum, having Hamming weight and stuff like that. This is like okay, we're looking at.
It's not as different as it looks. I mean,
Okay.
like if you restrict everything to Pauli operations, then this is kind of like Hamming weight, right? Because like you're saying, it's now the minimum number of bit flips or phase flips or Ys that you have to do instead of just bit flips.
Right. And this commutation relation, how do I see in the Hamming weight, like in the bit string picture?
Wait, which commutation relation? You mean like?
SI equals 0. I mean, is there a classical analog of this? Or is just...
There is, yeah. So you can map. All of this is kind of like a generalization of linear codes.
Mm-hmm.
And this E comma SI equals 0 is basically saying that your inner product with all of the parity checks in your linear code is 0.
Okay.
Yeah, so the commutation, like I think the precise thing is instead of the regular inner product, you have to work with a new one called the symplectic inner product, which is like somehow like it captures the fact that like an X commutes with an X, but it doesn't commute with a Z. Yeah, so that's how it generalizes linear codes.
Okay. I see. Thanks.
Sure. Okay. So let's draw some toruses. So the toric code is going to be an example of a stabilizer code. Where the qubits are going to be laid out in a particular geometric way. So they're going to be laid out on a torus. And now I am very bad at drawing, so this is probably going to be a disaster. But let's see if I can do this. Let's use a different color for the qubits. So the way I'm going to do it is I'm going to imagine I have a lattice in 2D. And then on every link in the lattice, there's going to be a qubit. So green means qubit. Oh, and there's. And then I'm going to basically say that this space is supposed to look topologically like a torus. So I'm going to identify, so you identify the left edge with the right edge, and you identify the top with the bottom. So like if you imagine, you know, you could take a a piece of paper, and then you could fold it, like if I take the piece of paper, identify the two edges this way, I get a cylinder, right? And then my paper is not flexible enough to actually do this, but I took the cylinder and I now identified the other two edges. I'm going to just crush this paper, but you can see I get a torus. So that's like geometrically how you get a torus, and then we're just gonna, we don't care too much about geometry here, so we're just gonna say I just identify the two edges. So like this cubit, like this cubit is gonna be literally the same as that cubit, and so let's put like maybe colors to annotate them. These two are the same, and then like this one is equal to that one. So that's the qubits. Now I have to tell you how to construct a stabilizer code out of them. So I have to give you some stabilizers, and the stabilizers are going to be defined geometrically. So there's two classes of them. One of them will be what are called the star or plaquette operators. So let me use blue for this. And they basically look like, so I'm going to copy the notation from Kitaev's book. So basically put an X matrix on, so a star is like, you have a vertex in the lattice. It's the four edges coming out of that vertex. So there's a qubit on each edge, and I put an X on each qubit. So it looks like. So I have one such stabilizer for every star. So I have one over here, and then one over here, and one over there, and so on. So those are the star stabilizers, and the other ones are called, well, he calls them face operators. Like people often use the word plaquette also. So this is now going to be a product on J in, writes it this way, so the boundary of the plaquette or face Z sub J. So a plaquette is just like, a cell in this grid or a face. So you're going to stick a Z on each of the four edges of that cell. So it looks something like this. Z, C, C, C. Okay, and that's basically it. So those are all the stabilizers of this code. So does anyone want to try to explain to me why these stabilizers commute with each other? Why is this a valid code?
Well, those two don't overlap. Go ahead, Youngman.
Is it because I mean, yeah, if they don't overlap, then they definitely commute. But if they do overlap, then they only overlap in two places. And since they anti-commute, if there's two anti-commuting things, then they just commute.
That's right. Yeah, that's exactly it. So yeah, if they don't touch, then they obviously commute. If they do touch, then they only overlap on an even number of positions, and so they still commute. So yeah, so for all, it's a different color. This should be C. They commute. and then I think you can check that you don't get minus identity, because there's just some, like, I think if you just take the product of all of them, you get identity that sort of, because every edge will show up twice, I think, if you take this product. And so everything cancels out. And actually, is it obvious why that implies you can't? I guess that implies that I is in the stabilizer group. Okay, actually, now I think about it, it's not entirely clear why minus identity is not in this group.
Well, oh wait, never mind.
Okay, I mean, one proof that it's not is that we'll eventually be able to exhibit like states that actually are stabilized by this thing. And maybe it's actually kind of obvious, because like all of the stabilizers are either all X or all Z. So any product of them, you know that they all individually commute with each other. So if you take any word out of the stabilizers, you can just move all the X's to one part and all the Z's to another part, without putting any phases in front. So it's just some product of X's and some product of Z's. And then, yeah, there's no way you could pick up a phase then. Like, you can only get identity, you can never get minus identity. I don't know if that argument made sense to anyone.
Yeah, that's fine.
Okay. Okay, so I've convinced Chinmay at least that this is a valid code, I hope.
Wait, what's stopping like all of the plus ones in the X part from perfectly lining up with the minus ones in the Z part? I mean, I believe you that it's a code, but I'm just
Wait,
curious
what minus ones in the Z part?
Like if you multiply all the X's together, you get some matrix. It has a plus one eigenspace and a minus one eigenspace. And if you multiply all the Z's together, or the other ones, X's or whatever, you also get plus one eigenspace and a minus one eigenspace.
Oh, I guess I
So-
wasn't thinking of it in terms of the eigenspaces, but just in terms of like symbols, like any word in the generators. Let's say it's like X, X. Oh, those are superscripts. Sorry. X, X, and maybe a Z, and then an X, and a Z. Right. I can first of all, like this word is, let's say I claim that it's minus identity, right? On the left-hand side, I can just put all the X's on the left and all the Z's on the right without any phases coming out in front, because every stabilizer commutes with every other one, right? So I have AX dot 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 AX, some U1 up to UK, AZ, or those were called S, weren't they? And then I have a U1 up to some UJ. And then I just look at the form of these things. Like every AX is like a tensor product of an X with an I, like some number of X's with some number of I's. And it's like on every position, like if I take this big product, in the end, I can only either get X or identity. Like I can never get minus, I can never get anything else. And then if I look at this big product, like on every qubit, I always end up with either Z or identity, nothing else. And then there's no way to multiply them. Like you can never have like X times Z equaling minus identity.
All right. You'll get like either Y, X, or Z, or identity.
Right.
In fact, there's something even nicer, that if all your stabilizers are just terms that are all pairs of X, so each term is either just a collection of X's or each term is a collection of Z's, you just pick the generators, you'll always guarantee that -1 is not an element of generated group, right? This argument wasn't particular to toric code. It was just the only thing Anand had to assume was that either a stabilizer generator is either completely X based or completely Z based.
Right.
Once you start mixing it up and getting a little fancy, that's when you can have concerns about introducing negative identity into your group.
Let me actually write that down here. So this is like a preview of the more general case that Chinmay will talk about. This is true for any CSS code. Okay, so I proved that it's a valid code. And now the next thing we could do is try to calculate what the dimensionality is, so to figure out how many of these stabilizers are actually independent. I kind of don't want to do the calculation because I'm very bad at counting, so I can just tell you the answer. Unless people want to do it, if you're okay with seeing me fall flat on my face. But the dimension of this code is going to turn out to be 2. Or sorry, the number of qubits. The dimension is 4. Number of logical. So, right, so we figured out that this is a, so let me call the side length of this code L. So it's on an L by L lattice. So the number of qubits you have, scales is L squared. I think it's like,
It's 2L squared.
it's exactly 2L squared.
Yeah, for every vertex, it has an edge to its right and an edge going down.
Right.
And there's a qubit on each of those edges.
Oh, I should say this, like 2 here, I think in general, like instead of using a torus, if you use some other surface, like this would be related to the genus of the surface. Because the counting that goes into this is like something like you start with the number of qubits, which is related to the number of edges, and then you subtract off. It's like this is equal to, it's like the number of edges minus the number of vertices minus the number of faces, maybe plus some constant terms in case like some of these things are non-independent of the others. But like this kind of quantity is like you know, this shows up in like this Euler formula, right? This is related to the genus of the surface you're living on. So that's where the 2 comes from. So like if you had a surface with more holes in it, you'd have more logical qubits. Okay, so that's the logical qubits, the physical qubits. The third parameter we have to calculate is the distance, right? So we have to basically understand what the logical operators on this qubit on this code look like. So let me draw the lattice again. Smaller one. And let me just draw the blue checks, which I think were X. Right there, X. Yeah, things that look like. So blue is X. So let's just imagine thinking about logical operators that consist entirely of Z matrices. So they're just like a tensor product of Z's with identities. I think you can probably show that it's sufficient to think of like just Z operators or X operators separately because of the structure that the stabilizers are either Z type or X type, which in my knows for sure. But yeah, for now, let's just assume that we're considering a logical operator that's all Z's. So the only, any Z that you do will always commute with all the Z type stabilizers. So we only have to worry about the X type stabilizers, which are these blue ones here. So what's the characteristic I need? So let me remind you where the qubits are, right? The qubits are basically on the links. And I'm going to pick some of these links, some subset of these links to apply a Z to. So what are the properties that this subset needs to have in order for the Z's to not anti-commute with any of these X stabilizers? Any ideas? Let's just try something.
Could you do every other horizontal line?
That's an interesting idea. Let's try that. So I'll do this row. And you said every other horizontal, every other link, I guess. So it's like that, and that. Is that you had in mind?
I was thinking you would need 2 Z's on every star, but 1 Z on every box. Wait, no, that wouldn't work.
I think the first thing you said is a valuable observation. I don't know that you can make it consistent with the second thing, but
yeah.
The thing about 2 Z's on every star is absolutely correct. That because every star is made out of X's, and the only way you can commute with these X's is if you have an even number of Z's on that star, right? So basically, you need either 2 Z's or 4 Z's. But you need this to hold for every star. So one thing you might try is something like, I don't know, like I could put a Z here, a Z here, and a Z here, right? Then what that'll look like is this star is okay because it touches that Z and that Z. This star is okay because it touches that Z and that Z. But now this star at the bottom is not okay because there's only 1 Z here. Right, and likewise, this star up here is not okay because there's only 1 Z here. So there's kind of an intuition behind this is that instead of just thinking this as 3 Z's, think of it as like a little string. And just draw a line along the edges where you've put Z's. So this string is yeah, basically, where did we have problems? We had problems at the the star at the bottom, and the star at the top. Which were the stars that occur at the endpoints of the string. Right? Along the string, you're fine because like intermediate points, you have like for every star, there's like a Z coming into it and a Z coming out. I don't know, is this kind of making sense? Like this picture of what goes wrong with the string? Does anyone have a guess now of like what kind of thing I might draw that doesn't have this problem?
Also, don't you want to close them into a loop somehow?
Yes, exactly. So that's what we're going to do. We are going to try taking a closed loop. So let's just take this loop, for instance. So on this loop, I put a Z on every edge here. And now you can see that because it's a closed loop, it doesn't have any endpoints. And like the endpoints are exactly where you run into trouble because that's where you have only one Z on the star. So here now, every vertex appearing along the loop, there's two Z's because you come into the vertex and you come back out. So this loop is a collection of Z's. So I'll just call this thing, this operator corresponding to that loop. I've shown that it commutes with all the stabilizers. So it's in the centralizer or whatever of the stabilizer group. So that was one of the two criteria for being a logical operator, remember? So logical was the centralizer minus the actual set of stabilizers itself. So does anyone want to guess, is this thing actually in the logical set or is it just in the centralizer?
Would it be the identity, so it wouldn't be in the logical set? Because it takes, yeah.
So why do you think it's the identity?
Because there's an even number of Z's in total, and I don't know if that's enough, but it seems as if like if you look at the three or all of the plaquettes that are affected, and you would like take, if the count is odd, it's -1, and you multiply those all together, you're gonna get 1, and so it's not gonna end up changing the phase of the total state.
Very good. So I think maybe a way, or the way I'd make the argument is as the following. So yeah, I think this that argument basically says that if you act with this set of Z's on any code state, you leave it unchanged. And I think a way to see that that's kind of nice is, as you mentioned, using the plaquettes, but you can just see that this loop of Z's is precisely equal to the product of 3 of the plaquette stabilizers. It's like the 3 plaquette stabilizers that lie inside the loop. So therefore, it acts as identity on the state. It's inside this group that's generated by the stabilizers. So it's not a logical operator. So like more generally, if I draw any sort of loop, you know, that maybe encompasses like a bigger region, you can kind of see that like if I just take the plaquettes that lie inside, you know, either I have a plaquette that's like totally inside and it just cancels with all its neighbors, or I have a plaquette that's like near the boundary and it contributes to the boundary and it cancels with the other ones towards the inside. But you know, the product of all these plaquettes will just give me the Z's on the boundary here. So yeah, so all of these like nice loops are apparently not logical operators. Anyone want to suggest what a possible logical operator could be? Preferably who has not seen what the answer is before.
since it's a torus, could you go off the edge and then come back around? I don't know if that would work.
Yes, that's exactly correct. So that's exactly what you have to do. So the logical operators turn out to be precisely the loops that wrap around the torus. So it's something like this string of z's here that goes off the edge and then wraps back around to the top. That's a logical operator. And then likewise, this string of z's that wraps around the torus the other way. That's also a logical operator. So basically, these are all the loops that are that aren't contractible to points. Like you can think of this operation of like multiplying by a plaquette as like it's a way to like shrink your loop. Like if I took this big loop here and then I multiply by that plaquette, I would now convert it to this smaller loop, and then I could do this one plaquette at a time until I shrink my loop all the way down to 0. But if I take a loop that goes all the way around, there's no way to do that. Like there's no way to shrink the loop to being a trivial operator. So that's it. The logical operators are precisely the non-contractible loops. And we did all of that for z. Turns out you can do it for x as well. It kind of works the same way, except you need to work with what's called the dual lattice, which basically means you just interchange the roles that vertices and like faces play with each other. So like an x loop is now going to look like, well, I'll give you an example of an x loop that is correctable, I guess. So I'll just do one that's not. So something like x, 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 like that. That is a logical operator. And this one you can think of as like wrapping around like that. And the reason it commutes with the stabilizers is that, remember, the z stabilizers were the plaquettes. And okay, that plaquette is like, goes around like that. But every plaquette here has 2 x's touching it. So, so it commutes with the x's. Okay, so we can see that this is also like another way to understand why there are 2 qubits or dimension 4, is that there are 2 loops basically. So there's like a horizontal loop and a vertical loop. So the 2 qubits and so the logical operators are going to be, let's say x1 is going to be an x on the horizontal loop. X on the second qubit, I'll just say, is x on the vertical loop. And let's say z1 is z on the vertical loop, z2 is z on the horizontal loop. By the way, notice that I flipped horizontal and vertical between x and z. Was that necessary? Like, could I have made z1 equal to z horizontal and z2 equal to z vertical? Chinmay says no. Anyone want to explain why it wouldn't work?
I'm not sure I understand what you mean by the logical operator. What is x horizontal?
Ah, very good. Okay, well, I'll explain what all these things are. So x horizontal just means any horizontal loop. So anything that looks like this string of x's here.
Right.
So
and like I guess you can go between any two of those using the stabilizers, right?
that's right. Yeah,
Because you can like shift them up and down or something.
Yeah. Yeah,
Oh.
so like for instance, here you could shift this one down by a row by just like applying the star beneath everywhere.
Right.
Yeah, so it's like you have like an equivalence class of operators under the stabilizers.
Right. Yeah, so I guess by x horizontal I mean any one of these operators that are all equivalent to each other. And x vertical I mean, yeah, any loop of x's going this way. So I guess it's something like that. That would be an x vertical. And then, okay, maybe the thing I should explain that's a little trickier is what do I mean by x1, x2, and z1, z2? Well, the code space is some four-dimensional space. So you have to map that onto the space you're trying to encode, like the space of 2 qubits. And then this is supposed to act as, like, say, x tensor identity on that four-dimensional space. And this is supposed to act as z tensor identity on that four-dimensional space. This is supposed to act as I tensor x. This is supposed to act as I tensor z.
By the way, so what happens if the, I mean, I don't know if you'll get to this later.
Oh, sorry. Well, okay. Mm-hmm.
All right, so William, do you want to ask something?
No, never mind.
Okay. So what happens if the torus is not torus, it's a ring?
Oh,
Is there only one encoded qubit or something?
let's see. So you mean you don't identify the top with the bottom, but you identify one pair of edges but not the other? Is that you have in mind?
Right. Yeah.
I think you get 0 qubits then, because I think the number of qubits is like twice the genus or something.
Okay.
Or
all right, because one logical XOZ will be destroyed from. Okay. Yeah.
wait, let me think about that actually. Maybe you still have 1 qubit actually.
Well, the problem is that the x, so your vertical contractibility now exists, and so now your horizontal x and z loops that you're going to get, they're always going to commute with each other, because right, if you notice that there are orthogonal sets of qubits, disjoint sets of qubits.
Right, so you can't even have 1 qubit because you can't even use the 2 horizontal loops to produce your 1 qubit.
Right.
Right. So what you get is you get these 2 additional logical operators, but they really aren't doing any much. The kind of object you should think about this as is sort of like you have one free qubit, tensors a fixed qubit 0, tensor another fixed qubit 0. Right? Those 2 extra logical operators, they kind of are working on those fixed guys on the side, but they aren't. The space that you're really working with is still remaining and it's empty. You know?
I kind of see. Yeah, I guess also that was a good question because I think it also answered the thing I was getting at with like why you have to switch horizontal and vertical here. Is precisely this thing that Chinmay said that any 2 of each other take horizontal loop that's on this row, and then maybe I take the Z horizontal loop that I drew here. They commute with each other just because they don't touch, right? They're on different sets of qubits entirely. And so they cannot both act as a logical X and Z on the same qubit, right? Because a logical X and Z on one qubit have to anti-commute with each other, because that's the action that they would have on a real qubit. So that's why for, and if you're saying X1 is going to be a horizontal loop, then Z1 has to be something that will anti-commute with that horizontal loop. And so you have to pick a vertical loop for Z1.
I don't know if you're gonna cover this, but what would be the significance of like diagonal loops? So like if you went around the torus by going up and then right and up and then right and then up and then right, you kept going.
I think, here, let me draw the picture.
Yeah, I mean, this is something I was kind of going to ask, was that couldn't you have something that doesn't just loop around the torus once, but like loops around it many, many times? As long as the lattice is large enough.
I think if you loop around, I think like the number of times you loop around is like, it behaves as like a Z2 thing, right? Like, it's like,
Oh,
if you
does
do
it?
it twice, it's like equivalent to not doing it at all, if I remember correctly. But
Oh, it's not a winding number. It's just a parity, you're saying.
yeah,
I guess that's basically what my question, because this is not obvious to me, but I believe it.
yeah. Let's do an example, I guess. So I'll start with Z. So I want to go up. Okay, if I go up like that, then I'm back here. And then maybe I go across again. And then this,
Just
I get confused with the boundaries sometimes.
and then just finish up on the bottom. Just like go across 3.
Across 3. So like this would be identified with that, right? Or no,
It's identified.
with that.
Yeah, it's fine. Yeah.
Oh,
Even if your thing went bigger, you could just.
wait, that one's not identified with that.
So
Is it?
the point, William, is look at now between these two lines that Anand has drawn, we have a kind of a shape, right? And if we looked at the stabilizers on the region between the two lines, we'll notice that the first line is equivalent as a logical operator to the second line, right?
Right.
Sure, yeah.
So if they're equivalent operators, and these operators all square to identity, you can see that they this net error here is just in the stabilizer group, right?
Well, I think one way of seeing it was that if you looked at the picture Anand drew, and you went to like the bottom left plaquette, and you just applied the plaquette stabilizer, that would, I think, kill the left and right boundary, and then add a new boundary on top and on bottom, and then you would just get, I think, a closed surface.
Mm-hmm.
I guess I had drawn this edge, right?
Yeah.
Yeah. Because you're saying you applied this plaquette.
No, the one to its right.
The one to this one. Okay. Ah, right. So then that will kill the left and right, and instead you get something here, something there, and then you have
But I think this is like slightly drawn incorrectly.
Probably.
So
So
maybe
sorry
once
to
you
jump in. I think you can. I think you can do it. All you need to do is to connect to connect them all. You need one like length 3 line at the bottom. Maybe I'm too late. But if you draw the length 3 line at the bottom and then put part of it at the bottom and part of it at the top, you get a closed surface.
See, wait, I'm gonna draw a smaller thing where I can identify. So these things are the same.
So Anand, maybe it would be helpful actually at this point if you eschew the grid and just draw on a torus. Quite literally.
Oh yeah.
Instead of drawing the grid, just draw a big square, and we'll just imagine that at a fine enough pixelation, this is actually a path on the grid.
Sure.
So now it'll make it a little easier to draw. So now
That's a good suggestion. Because
now
the thing I'm
maybe
getting wrong
question-
is just the discretization at the edges.
yeah. So imagine at the pixel level of Anand's pen, this is actually a well-defined path this way now.
So you go like that, and then that takes you down to here, and you try to keep going.
And now take that point and maybe just finish up somehow. Come back, like even on the physical body itself, you could.
Yeah. Let me just start this from a little bit higher up. So this eraser is really weird. But yeah, so if I start a little higher up, that comes back over here, and then I could go like that.
I don't want to do that now because you wound around the other way.
Oh,
Like I think you need to cross coming back.
I see.
Well, it's fine. All of these kind of things can still be analyzed.
Yeah, but I guess it makes sense that you want to keep the winding number horizontally 0 for this example.
I guess this is the sort of thing where we could like assign this as homework
Like
for
that.
ourselves, and then someone could post to the reading group email list when they figure it out.
As a simple example, what if you just did the diagonal? So that still just winds around once, but diagonally.
I think that's going to be a product of probably an X loop and a Z, like a horizontal loop and a vertical loop. You mean like something that goes like this, right?
That'd be my guess too. But it's a bit hard to
If I draw, is this visible?
I can probably stop my screen share and then you can do a screen share. I think that's probably how I should do it.
Chinmay, are you talking? Oh, you're muted right now.
Now can you hear me?
Yeah.
Yeah.
Okay, so if I look at the blue operator and the light blue operator, right, they are going to be identical because they are differentiated by that small purple region. So those two operators are identical. Now I could, go further even and sort of extend that purple operator, till it kind of came like this all the way, right? So now I'm able to get to this operation kind of looks like this diagonal, right? So now I have the teal colored operator and the blue operator are equivalent, right?
Right.
Okay. So now let's push the other direction. Let's add another purple region that goes all the way this way. And now I can take that the blue operator and instead push it around so that it looks kind of like this, right? Okay, so does that kind of make sense?
Yeah, just to check, the thing you just drew should have been blue, not teal.
Yeah, so
Really?
I have blue and I have
Teal is
teal.
like the pushed operator.
Right.
So this
Got it,
is like
got
the diagonal composed with like a horizontal loop or something, right?
Exactly. So now, if you notice, what I've done is I've shown that teal, right, plus dark blue, right, is equals 0, right? They are the same guy, right? Because I just moved them by stabilizers and I showed that the teal and the dark blue are equivalent, right? And now if I look at what I did is I saw that this guy was a diagonal plus a horizontal, and this guy was really vertical, right? So therefore, diagonal is the horizontal plus the vertical. Maybe that's the easiest way I know how to see it.
I guess all the addition here is like Z2 addition.
This is all just Z2 addition because I'm just adding stabilizers. You could start any way with any of these objects and sort of go this way. And then with the picture you'd drawn earlier, right, you had sort of done some kind of fancy looping that looked something like this, right? You went red to here, and then you went from here back, right? Something like this.
Yeah.
Now, I claim that the easiest way to look at this is there are 3 overall horizontal loops, right? I start at the top and go up horizontally, and I go vertically. So I should be able, and one horizontal loop this way. So I claim I should be able to prove that this is equivalent to this object that looks just like a cross that looks like this, one going this way and this way. And the easiest way to prove that would be to start deforming it towards that. So I could start deforming it by, adding this region here, which would move my blue, instead of being the blue cross, now that blue cross has this red edge, right? Then I could start moving the other regions, and it would take a little bit of time, and I'm sure I'd mess it up if I'm doing it live on the spot, but I'd overall be able to show that this thing is equivalent.
Right.
So Chinmay, that's not a single horizontal line or vertical line, that's a product of
This blue one?
Yeah, in the second picture, like this wind.
Yeah, it's one horizontal line plus one vertical line together.
So it's like a joint logical operator on the 2 qubits.
Yeah, so this would be a logical operator in both.
I see.
It's like a Z.
Like a logical Y on the first qubit or something.
I
see.
Not necessarily. Right.
This is just Z times Z. Right?
All right.
So this should be, whoops, Z times Z. It's a very long first.
I see. So if you wind around like 10 times, you get identity. But this is three windings.
Yeah, I mean, the easiest way to sort of look at this is, okay, if you want, I can show you how to do this picture with make it a little easier. So let's just start off with the two red regions that go this way. And just starting off with those two lines, I claim that they should be equivalent, right? They're equivalent because this middle region between them, if I multiply, I should be able to cancel them out.
Right.
Take that middle region and sort of cancel them out. And that what that'll give me is that since the two red regions are equivalent, I can just simplify this picture by removing two of them very quickly. So I directly take this picture and I remove those two, and I can then just keep working.
Okay. Thanks.
Thanks.
I guess I'm still not satisfied entirely because so I'm looking this up, right? So the fundamental group of the torus is isomorphic to Z cross Z. Okay, Z is the integers here, not the poly Z matrix, of course. Like, doesn't that mean you should be able to just loop around infinitely, and that there's no way you could continuously deform that into a single loop?
Okay, so good. So the fundamental group is the non-abelian group, so that's the homotopy of the object.
Yeah.
What I'll talk about next week is actually, this is fundamentally related to the homology of the object, which I believe the homology type of the torus is Z2 cross Z2.
Okay.
So yeah, so that's a good question. So yeah,
But because to me it sounds like you're just saying you're deforming a loop into something else, but that should not be possible.
Mm-hmm.
I don't know. I guess we'll talk about this more. Maybe we've kind of gone off track here a bit.
Yeah, so right, so there's a difference in the homology and the homotopy, where based on abelianization, basically what we want is that what we're going to achieve here is that these two logical loops are equivalent, even though going around, even though they go around this twice, right? I think I'll explain this maybe next week in greater detail, starting with a bit more of an algebraic starting point rather than.
I guess we're nearly out of time. I just had one other thing I wanted to say about the toric code, just this quasi-particle picture. Maybe I'll just say 10 seconds about that, and then if I can get this sharing to work.
Someone's unmuted and talking about bipartite graphs.
And now what's the need for a pair, which means that this cell.
Is there a way we can mute everyone?
And you can just click on them and mute them.
Yeah, you can
okay.
selectively mute.
Okay, I have to figure out who it is. Yeah, I'm like this grid view where I can't see. Okay, I think I know who it is now. Mute. Okay, now they're all muted. So, okay, and you can still see my screen share, right?
Yep.
Okay, so I'll close with the quasi-particles things. So, yeah, okay, I guess the way to think about this is, if you think about say an error occurs, say, here's my torus, and an error occurs, so an example of a correctable error we saw was just a string of z's that has endpoints. right? This is an error because it takes us out of the code space. It anti-commutes with some stabilizers, but it's correctable because it doesn't loop around. So how would we actually detect it? Well, we'd want to do this syndrome measurement, right? So for every vertex, we'll measure the star. And for every plaquette, we'll measure the z's on that plaquette, but those don't matter because this is a z error. And then the only stars that will give us a sign that something is wrong is the star at the endpoints of the string. So this quasi-particle point of view is sort of, you can think about these things as like, well, you can think about the whole toric code as actually a physical system with a Hamiltonian. And what is the Hamiltonian going to look like? It's just going to be a sum of, for every star, identity minus AX star, sum for every cell, identity minus AZ. So this Hamiltonian is just chosen so that its zero energy eigenspace is precisely the code space. You know, a state is in the code space, if and only if. And now if an error occurs like this one, you can, first of all, interpret this error state as being an excited state of this Hamiltonian. So it's some state above the ground state. And here it's going to be a state with energy 2, right? Because you get energy, you get like one of these terms, you know, for each of the stars is going to be violated. So you get an energy cost of +1 for this star and +1 for that star. So here, psi h psi is equal to 2. And so these things here are called quasi-particles. And you can think about, so first of all, you can like completely diagonalize this Hamiltonian. Like you can understand what all the eigenstates look like. It's basically just like all the different patterns of like different places you can put the quasi-particles, or different like stars you can violate, or plaquettes you can violate. But you can also like use this to think about dynamics. Like say prepare a code state and let it evolve over time according to this Hamiltonian, or maybe this Hamiltonian plus small perturbations. And what can happen is like an error can occur, and whenever an error occurs, you create a pair of quasi-particles. You generate two ends of a string of z's. And then these things can move around with basically no energy cost. So once you've created a string like this, you know, this state has energy 2, but so does, you know, the state where the string has now moved all the way over there, and now the violated syndrome is up here. This thing also has energy 2, because, you know, again, you're still just violating 2 constraints. So that means that it's like relatively easy for this state where you had these 2 violations to evolve into that state over time. And then ultimately what can happen is that if you have an error that starts as like a little string, looks like that, the 2 endpoints of the string will like float around, and eventually they'll loop around the torus. And then you're screwed, because now your error that started out as being small and correctable has become a genuine error. Like it's actually corrupted the state that you have. And this can happen basically relatively quickly, because the energy of all these states, no matter how big the string was the same. So, so this is like, it basically says that the toric code is bad as a self-correcting memory. Like, it's not like you can prepare a code state and just let it sit there and hope that it will remain good. So you have to do active error correction, or else these errors could grow very quickly. And there's also this perspective of these things in terms of anyons that I don't really understand too well, that like you have you have one type of quasi-particle for the Z strings, right? And then there's also the X strings. Now those will, like an X string will violate the two plaquettes at its endpoints. So then, for each plaquette, you have you can think of it as like an X particle. And then, these particles interact with each other in interesting ways. So the interesting thing that happens is that if I take these and I loop them around each other, I'll get an overall phase of -1 on the state. Because what will happen is that this blue string is going to have to cross over the red string, which means that you're going to have to multiply an X operator times a Z operator, or commute an X operator past the Z operator. You'll get a -1. And that's, yes, that's, when you have particles that when you exchange them this way, you pick up phases, those are called anyons. And so that's the connection there. But I don't really have anything more to say about that. Hopefully we can get an actual physicist in one of the future sessions to explain it to us. Yeah, that's all I wanted to say about the toric code.
I guess one thing that might be worth mentioning is, I don't think you ever explicitly said it, just the distance of the code being root n.
Oh yes, very good. Yeah, thanks for reminding me. So the distance, we had to calculate what the minimum weight logical operator was, and it's sort of clear that the minimum weight logical operator is just like you take the smallest loop across the torus. Where will I write it? Just write it here. So the distance, the minimum this minimum weight is just the side length. So you have a code with, was it 2L squared, 2, and the distance is the side length. Or if you reparameterize it, it's n physical qubits, 2 logical qubits, and square root n over 2 distance.
Let me ask another question, just while I'm waiting for other people to ask questions. When you were reading around, did you get any intuition of how Kitaev came up with this?
Yeah, people mentioned that he was thinking about, I think the anyon picture came first. Like people were thinking about some other systems with like quasi-particles that braided around each other, and he was inspired by that to come up with this. People use the word semyon, I think, to refer to these things. Just to throw out another random fact, like another thing that I came across while reading is that condensed matter physicists are apparently bothered that like this Hamiltonian looks very unnatural because it has like these weird 4 local terms. And so there's this other thing by Kitaev that's like the Kitaev honeycomb model or something, that apparently the reason people care about it is that it's a more natural looking Hamiltonian, but in some low energy limit or something, it simulates the toric code, I think. So yeah, this is really out of my depth here, but yeah, if anyone knows about that and wants to explain it, I think that would be a cool topic for future class.
Okay, well, thanks.
Thanks.
Yeah, thanks, Anand.
Chinmay, before you leave, so you're giving the talk next week, right? Would you mind at some point suggesting a reading for us? Maybe you could like send it out to the group or send it to one of us.
Oh, yeah, that's a good idea. My intended sort of topic will be to take this idea of toric codes and generalize to look at codes as equivalent to really topological objects called chain complexes. And we'll see that, and then we'll talk about how to construct chain complexes. So there might be like, it might be something like read section 1 of a certain paper or something like this, but I'll let you know maybe by tomorrow.
Okay, great. Yeah, that would help.
Okay.
So I can stop the recording at this point too. Do I have to stop the share first?